I'm Jesse Beaumont. I'm the CTO at Tensile AI. Today, I'm going to talk to you about the Data Lakehouse and why we believe that, along with Databricks and Delta Lake, is a key to success for value-based analytics and alternative payment models. I hope you are enjoying Spark AI Summit. Please leave your questions below in the chat box. My background is in computer science and data analytics. I've been a software developer for 20 years, first at SAS working in R&D, and for the past 10 years as a consultant with clients in the health and life sciences industry to deliver enterprise analytic solutions and support cloud initiatives. Tensile AI helps health plans and health systems implement advanced analytic solutions in 4 main areas: value-based contracts, risk adjustment, marketing analytics, and machine learning as a service. And our solutions fully integrate with one another. So self-service BI, visual analytics, ad hoc analyses, augmented analytics, and predictive models are surfaced through a common UI and an API that we call HealthPlanIQ. We are a Databricks partner, and HealthPlanIQ uses Databricks as the core technology for data processing and to support governance across our products to combine new sources of data, like social determinants of health. This allows data to be leveraged quickly and easily across various stakeholder groups. In fact, the demo we will show today is one where we bring in some useful SDOH data to produce a better risk model. For those unfamiliar to healthcare, value-based care is a mechanism to pay for healthcare services in a manner that directly links performance to cost, quality, and the patient's experience. And payer organizations and health systems contract with one another to improve outcomes and reduce medical costs. Providers are incentivized through a disbursement of any shared savings. When you analyze performance of a value-based contract, you're looking for ways to identify and improve health outcomes and reduce costs. Examining the drivers of quality and financial performance takes place between health plans and provider organizations. And any analytics platform being leveraged needs to be able to handle large data that is continually expanding and changing, and gauge the quality and usefulness of new data. This is so you can govern whether it needs to be routinely collected for reporting and analytics around the contract performance. This slide illustrates typical data inputs and analytic outputs associated with a value-based care arrangement. The types and volume of data needed to be processed is quite extensive. We're showing just a subset of all the sources on this slide, and new data sources are continually being added. Data pipelines are always having to adjust to previously ingested data as often and as fast as they are absorbing new data. And each update contains restatements of claims, encounters, enrollment, and attribution. And these restatements need to be both auditable and quickly accessible for analysis. Using typical data warehouse and data lake constructs, it's difficult to manage this. Extensive ETL processes reconcile this data depending on where and how it is stored, whether in a data warehouse or a data lake. Metrics and heuristic rules are not consistent among source systems, and there's often disagreement or misunderstanding on how to interpret specific data sources. This generally leads to the development of independent, yet overlapping data assets whose use is not governed properly. There are often disparate answers to the same business questions and frustration around trust in data. Thus, we see the need for the emergence of the Data Lakehouse as the foundation for analytics and thus data governance in healthcare organizations. Here we see a typical, rather simplified data and analytic environment for a health plan. The source data is read, manipulated, cleansed, verified, and loaded into a rigid data warehouse schema for SQL consumption. Or the data is replicated, stored, and ready to be applied toward meaningful use in an ad hoc way from a data lake. And some phases are very demanding of the already limited resources. For example, interim data from ETL processes that churn through the data consume a lot of shared network disk space. And with the data warehouse, the cost of data extraction, cleansing, and reshaping this data is spent up front as data is ingested. Propagating new assets to the model follows a software development lifecycle process for most organizations, which become looked upon as slow and inflexible. And organizations implemented data lakes in the hope of overcoming some of those challenges and limitations that the data warehouses were facing. With the ability of alternative data sources and the rise of advanced analytics, data scientists were capable of doing their own sophisticated data work. The EDW had become an impediment to innovation through analysis, and the data lake became the darling of the data science world. And for a data lake to be successful, adequate computing power is essential. Also, data lakes gave clearance to the store all the data you can find practice, which hindered data governance. And this necessitates the need to rethink the appropriate architecture for healthcare, one that combines the benefits of a data lake and a data warehouse into analytic applications that can produce far greater insights and modeling capabilities than their BI predecessors. And if done correctly, the Data Lakehouse will serve as the foundation for data governance by enabling easier integration of analytic applications through a common API. It ensures standardized use of new sources. And healthcare organizations can't realize the full potential of these models until they deploy a unified technology platform. So what does this unified platform need to do? Well, at a high level, it must be able to rapidly ingest new data and improve the speed and governance around that data into existing reporting assets and predictive models. It needs to store and combine comprehensive data, analyze it, and provide interventions in real time and integrate feedback. And each need here is rated on how easy it has been to achieve with the old systems. It needs to be able to ingest and use both structured and unstructured data. We must be able to tailor it for the needs and capabilities of various user groups within and possibly external to the organization. It needs to scale to ongoing changes in needs. It needs to be capable of handling large files and many concurrent users. And it should save time and reduce the overall cost associated with producing analytics. We want to avoid a steep learning curve, so it should be familiar to the user base without needing to learn a new language. It should facilitate the data governance process to standardize data availability, usability, integrity, and security. And operationally, it needs to ensure the data can be trusted and doesn't get misused. And as you can see, we do not get many of the things we want in the old system. Now here is HealthPlanIQ with the Databricks Data Lakehouse. New data sources can be introduced quickly and easily. The data science teams are provided with various tools and languages to analyze that data and identify what is important. Then, with Delta Lake, institute the schema, the process for ingesting data ongoing, and publish in a controlled manner. The data does not need to be copied or moved again. It behaves like a transactional store, and solutions such as HealthPlanIQ can securely connect directly into the data lake. We believe this new architecture is essential for healthcare organizations because it allows for easier testing and integration of new valuable streams of data. It overcomes the limitations that have labored organizations that have essentially kept storage, compute, analytics, and governance siloed under the data lake model that became so popular about a decade ago. Databricks Connect makes it possible for our solution to run Spark remotely on Databricks and integrate with a high-performance platform. And now HealthPlanIQ can consolidate and provide value-based analysis by concentrating on the analytic need and not get stalled with data management tasks. If we go back to the factors I mentioned a moment ago about what is needed in that next generation platform, we see here that using Databricks and Delta Lake to create a data lakehouse and combining it with an industry-specific API, in this case, HealthPlanIQ, gets us almost everything on our wish list. And now let me transition over to my demo and show how the concepts I just went through are fully realized using Databricks. What we are looking at here is our product, HealthPlanIQ, which, as I've mentioned, is built on top of Databricks. And along the left side are the various solutions that make up HealthPlanIQ. And each solution is fully integrated with the others. There's a sizable amount of data, and we process this data on the fly to surface endless combinations of reports, visuals, or predictive models. So there's obviously a lot of moving pieces. And using the data lakehouse is really what enables that integration to be successful. Viewing our value-based analytic product, the top panel is showing a trend of claim cost and average member risk scores over time for a specific cohort. The risk scores you are seeing are derived using only claim data. But there are better ways to predict risk using non-administrative sources. We will show how we can bring in and store a tremendous amount of new data. In this case, it will be social determinants of health information. And ultimately, we will be able to use this data quickly to add valuable insights to a new calculated risk score. In view here is a Databricks notebook used to work on our new risk score. Databricks notebooks allow me to operationalize my ETL and ELT processes. I can use existing data sources and apply changes directly within the notebook. And they can be versioned, shared, and allow freedom of exploratory analysis. It is essentially a fully interactive development environment. Here we will integrate SDOH data. And social determinants of health are the environmental conditions that affect one's health. And as we go along, we'll revisit the benefits inherited from our Data Lakehouse model. So Databricks provides a full-featured API that allows me to browse the file system using familiar idioms such as LS. Here we see many files which have already been imported into the Databricks file system. And we're going to add 3 more SDOH files: census, housing, and transportation. I browse the data and then choose Add Data. To upload to DBFS, I'm going to establish my target folder. And then I'm going to drag the files over for census, housing, and transportation. And now the source files are now in my local file system in Databricks. Our 3 new files have been added, and returning to our notebook, we can refresh our file listing. And we all confirm that our files are now available. Now that the raw source files are loaded into DBFS, we can read their contents and review the included data. We see that the SDOH census data contains a RUCA code associated with zip codes. The housing data includes a lives alone indicator. And the transportation presents details around access to a vehicle or public transportation and distance to care. Here, I have used Spark to ingest the raw data into the data frame, display the schema, and persist the new data into a Delta Lake table, which will enforce that schema. An enforced schema ensures that the data types, contents, and referential integrity are kept. However, it is also possible to evolve changes as needs progressed, such as new columns. And also with Delta Lake, the data is versioned. Traditionally, data versioning had to be done programmatically within the data itself. A quick reflection on the warehouse over the years, it's not atypical to include a table in the warehouse that is solely for versioning, not only for tables, but within rows. Various methods, such as type 2 and type 4 versioning of records, was part of the normal process to manage volume, consumption, and the ease of use. And now there are direct API calls which report on the series of versions of metadata. Back to our use case. With the ability to code SQL, Python, and other languages, document in line with Markdown, and work interactively with the data, the transition is fluid. The data science team can easily interact with the new data and join it with tables already in the data mart. And queries run extraordinarily fast on the platform. I'm not having to labor through I/O limitations or re-instrument SQL as pass-through with potentially proprietary syntax so they would run optimally on their native system. Also, this is SQL syntax, so I'm not having to learn anything new. The data scientists have conducted their exploratory analysis. And they've determined that 2 variables, RUCA code and lives alone, from the 2 of the tables we brought in are going to be used to calculate our new risk score. Now let's walk through our steps. I've combined my member attributes such as zip code and hierarchical condition categories from other models. And since cost is a dependent variable, I can reach into the claim data already in our MART on a per member basis and bring in their allowed amounts per month. Then I bring the two temporary views together. A quick note on temporary views. They are lenses used to piece the data together without creating redundancy. And the view definition is not written to the underlying metadata. They evaporate with the session. I can share them across sessions as well by making them global. So we've prepared the member data with the variables that the team has determined are needed for the new score. So now what? Well, the data science team has built the new scoring model and defined the logic in a shared Python user-defined function. To utilize it, I can convert my data into a data frame and continue the work by coding in Python. Then I use the scoring module they've produced and maintained to attach the new SDOH risk score to my data. Because much of the work we do is migrating legacy SAS code, and with a data lake, including raw data, is likely to contain raw SAS date values. Continuing the code in Python, I can pass the data in place to convert from state integers into concrete dates. Now we can update our changes in our data mart and then refresh to our view to enhance our trend report. Here I'm including the SDOH risk score in an already defined view. Revisiting our provider sphere risk trend, we see our old risk score in red. And now in blue, we see the new SDOH risk score, which has been seamlessly introduced and is more representative of the true risk to the member than the one we used before. The Data Lakehouse has granted me the freedom of a data lake with the constructs of an enterprise data warehouse. Data governance has easily been realized, reliable, and routine. The schema is enforced but malleable. The data is versioned and auditable. More meaningful analytics can be realized with more data to analyze performance of value-based contracts. Thank you and enjoy the conference.